So the talk that we have today is going to be broken into three parts, and we have three different groups of people that are going to collaborate on this. It's going to be an overview of a little bit about SCinet and the SC17 conference network, and it's specifically going to be about the DevOps group, which is sort of a hybrid group that handles both server administration and software development. And we have three sets of speakers. We have Ken Miller from Penn State, who's going to be starting us off. We have Neil McKee from the InMon Corporation, and we have Trevor Goodyear and David Ediger from Georgia Tech Research Institute that'll be talking last. So without further ado, I'll turn this over to Ken, and he'll give us the overview. So thanks, guys.
All right. Thanks, Jason. Pretty much the DevOps group was a merger of the IT services group and a measurement group within supercomputing SCinet. The IT services group mostly handled general IT services and network protocols, things like that, and VM hosting. And then measurement group really handled anything from network statistics and monitoring measurement performance. So the merger of that was really as switches and everything become more software-based, Linux-based, that there's more opportunities for automation, as well as being able to handle things dynamically the way SCinet demos could go, or anything based on network research. So pretty much went through that there. There's a link there to the SCinet page for this year as well if you want to see this. I want to see if I got this acronym right, but it's typically 2 years to plan SCinet for the conference, about a month to build it, about a week to run, and about 1 day to tear down. So it really it's kind of like, planning for Thanksgiving dinner. It just all goes really quick, and then, but it takes forever to plan it out and take from there. So it's actually a lot of fun to build, one of the largest and fastest networks in the world, and then be able to experiment and do some things that you can, take home to your home institutions, and then also be able to look and deploy and collaborate with other people. So it's pretty good and enriching experience. So like I said, DevOps is a merger of measurement and IT, and currently there's around 15 people on the team, with 2 students and 1 women in networking candidate as well. So a scholarship program within SCinet. Typically IT services handles DNS, DHCP, NTP, anything related to network protocols. They also handle the intranet for hosting, as well as the content management system or customer request system. If you're going to be on the show floor, whether you're a university or a corporate sponsor, and you want access to the supercomputing show network, you can request that in your booth. There's Wi-Fi available, but if you're going to be doing any large demos, anywhere up to multiple 100 gig connections for your booth, it can scale up that high. So it's pretty amazing, some of the stuff we can set up for people. So I think the biggest request this year is 16 100 gig connections for one booth. So it's pretty amazing. We also do some VM hosting and everything internally, running a KVM. We also, for most of our own services, as well as other SCinet teams, like security has a logging server and some other security tools they run on top of our VM hosting. So it's a matter of cutting down some of the silos and stop the duplication within other teams to try to merge this team together and go from there. On the measurement side, mostly SNMP is done through Libre NMS. We do some stuff with PHP weather maps and some applications monitoring through SNMP. We've used XYMon in the past, and Graphite and just other tools. I think Esmond was used years ago. But like I said, moving forward, it's just standard SNMP stuff. For flow collection tools, we do SFlow, NetFlow collection, IPFix, using InMon's tool, which Neil will touch on a little bit, as well as the Georgia Tech tools. In addition, InMon's sFlow-RT tool is a real-time analytics engine, and also Host sFlow is a Linux and Windows-based push agent for system metrics, as well as host-based application metrics. And the Georgia Tech tools will be talked about in a little bit as well. So monitoring, we do a set of measurement displays around the show floor to kind of explain to people what's going on. We do individual dashboards for booths or demos that are happening, as well as an overall a real sFlow-based weather map that's updated in real time. You can highlight on any link, and it'll show you what's going through that link at any particular time. There's also Nagios pieces with booth up-down status. We call it the red-green page. And there's some other statuses on WAN links, as well as a router status, and just different things like that for just general up-down monitoring. In addition, there's different displays we'll put up. Just really depends on what content and what we're measuring that year. It can be anything. I think last year they did a wireless heat map. Georgia Tech was able to pull some of the NetFlow, sFlow data and build their own heat map as well. Among the booths, the wireless heat map is really where wireless try to triangulate wireless users on the show floor, and kind of see where the busy parts of the network or busy parts of the show floor were. We've also done some stuff with RIPE, showing where ping latencies around the world for IPv4, IPv6. Security has a page like clear text passwords, and some other security concerns. How many wireless has one with conflicting Wi-Fi SSIDs that are not part of the show floor that people are hosting themselves, like through either local access points or mobile devices, things like that, that might conflict with RF. So they have a kind of a wall of shame for that kind of stuff. But anyway, there's quite a bit of information we can display on some of these things. Really just depends on the use case and what information people are interested in seeing. From the network performance side, last year was our first time we actually set up a 100 gig Mellanox card and a Dell server. So we had a 100 gig Persona running. So we did quite a number of tests with that. We actually were able to set that up over multiple VLANs to be able to take that one server and scale it out to multiple measurement points to test different demos and whatnot. In addition, there were 3 10 gig Persona servers we have deployed around the show floor. We also have an NDT host running for speed tests. We also have an OAP server running with an external CDMA clock source, so we can have a clock source on the show floor. In addition, with Persona, we've done Mad Dash displays depending on where traffic's going to and from. We want to be able to set up that to different sites, both internal and external, depending on where traffic's going or being sourced from. In addition, we have an experiment going on with a PS Flock, which is comparing standard servers to small nodes. Like we've used Raspberry Pis in the past, and we're using I think it's called Leva boxes now that are a couple $100. We're experimenting on bandwidth and latency measurements, with large servers as well as small devices. Something new we've taken on after the merger was in SC15, we actually were able to do some SDN implementation, pulling data out of the customer request database. We created interface templates, and we're able to do booth demonstration, booth interfaces, pushing that out through an open daylight controller. And we got that running for part of the DNOX. I think about half of them were running this. Last year, we were able to do the same thing again, except they switched over to the Ryu controller. In addition, last year, they created a custom bandwidth scheduling application for different network research exhibition demos that were happening on the show floor. These were coordinated through our database, a scheduling application or a scheduling template they built, as well as being pushed out to course of switches to be able to take one network and be able to use it for multiple demos at different times. So you would really get a time slot for your bandwidth. So I'm trying to think here. They wrote an agent to query the CRS database and set up correct paths, QoS, for the given demo time slot. So we're able to custom tune this with really 3 different sets of data and different groups coming together to be able to deploy something like this. So it was an interesting mix. And then here's kind of a layout of, the show floor, what they were able to do last year with the bandwidth scheduling application. Well, we can get into different details of that or context directly. We can go into details on that, but it was a pretty interesting project. So then other SCinet teams that really, if you have anything related to IT and you want to do it in an R&E field, we probably have a volunteer position for you. So here's a list of the number of teams. And like I said, if it's a day job or something you're just interested in, there might be an opportunity here for you. So that's really all I had just for the overview. Neil, you want to take over now?
Okay, I will click share screen. Make sure this is a possibility. Share screen.
All right, we can see you, Neil.
You can see. Okay, so I'll click that. And we're off. Okay, so Jason invited me to talk about the flow monitoring at the show, and he asked me to particularly touch on scalability issues, because that's often what's most interesting about the SCinet network is what are the different ways in which you run into things you've never seen before in terms of scalability and the challenges. There's also a challenge in monitoring such a diverse multi-vendor network. And I'll dive right in with the diagram of the architecture for last year. And we'll show a little bit about what we've been doing. This diagram is actually animated with real-time traffic data, but it breaks down roughly like this. There's an optical layer where we connect to various WANs. The core has switches and routers in the middle here. Those are the big boxes. The distribution layer, we call it DNOC, has separate sort of mini booths dotted around the show floor. And those are the ones where the actual booths will connect to. Then on the other side, you have the commodity network, which is where all the Wi-Fi access points connect through into that one big Juniper router. And we're also monitoring the various servers that are being used in the NOC for one thing and another. So if I gray that out, one of those servers has a virtual machine which is running the Traffic Sentinel and sFlow-RT application. And we're getting NetFlow from the Cisco and Juniper routers and sFlow from pretty much everything else. So the DNOC switches, the commodity switches, some of the core switches, and we're also getting sFlow from the servers and hypervisors that are being used as well. And in some cases, sFlow even from the booths. So what's a part of what we'll talk about is how the DevOps team is supporting booth demos and exhibitor demos, and they can just turn on their sFlow feeds and point them all to the same collector. And the graph is an SVG graph that's being animated by sFlow-RT. So any changes in the traffic patterns will change the colors on the links. And if you click on it, you can get real-time traffic data. This is the public-facing version that just gives you sort of top protocols, but privately within the NOC, you can see, top talkers and VLANs and whatever is useful for actually understanding what's going on. And this graph updates on a per second basis, so it's kind of instantaneous. So here's an example of an exhibitor demo. This is the Osiris distributed storage demo. And here you've got sFlow agents running in the show network and also running host sFlow on various servers in different locations around the country. The WAN bandwidth is very high, but it actually doesn't need very much bandwidth to get the measurement data back to the show. And that's before the links change color in response to traffic changes that can be clicked on for instant traffic visibility. So it's really fun to do this as a DevOps team to actually help exhibitors highlight what they're showing. Now, to get back to the scalability question then, this year we actually finally topped 3 terabits of switch-off packet switching data. And you can see that in the first graph on the top left. It's a little hard to read, but actually pretty much all of it was being monitored with the sFlow. So the NetFlow data was really just people checking email through the show routers. Most of the heavy lifting is being done by sFlow here. And that's also why we can break it out by VLAN and MAC address, full stack protocol decodes. And Traffic Sentinel is also merging in BGP and DNS data and applying network-wide deduplication to avoid double counting when the same traffic is seen in 2 places. So the question I'm hoping that you're thinking is, why does it scale so well? How can you monitor 3 terabits with a VM and still get that full stack visibility? And this question comes up a lot, so we have slides to describe the difference really between the NetFlow and the sFlow approaches. So that's because NetFlow is very familiar to most people, and the simplest way to think about sFlow is to put it alongside and show just how much more radically simple it is for the switches to implement. So whereas in a NetFlow implementation, the router has to decode the packet, build a flow cache, and flush it and send aggregated records. And a switch implementing sFlow just streams telemetry in terms of counters and then sends the hardware sample, packet samples directly to the collector. So a good way to think about it is all of the steps after that, the decode, hash, flush steps are all just moved to the collector. The other thing that we're taking advantage of in the show network is that there are layered sFlow agents for different kinds of sending. So we can get data from routers, switches, but also from servers, hypervisors, virtual switches, VMs, containers, and even some applications. And so I'll talk a little bit about what we're doing with that to extend the visibility further up the stack. Another question that comes up that Jason wanted me to touch on is a different kind of scalability in terms of the number of senders. So I thought I'd just throw up this picture. This is part of a network with about 2,000 switches, all sending sFlow to one Traffic Sentinel server. And the largest is actually about twice the size of this one that I know of. You can look at any link to see the traffic patterns, or get the deduplicated traffic matrix for the whole network. The scalability also extends on the server monitoring side too, pushing the 100 counters from the servers in one binary telemetry block, every few seconds is actually a very lightweight thing to do. And from the point of view of the collector, it's really just about the same as monitoring one more link in the network. So it's quite straightforward to examine clusters, either individually looking for outliers or modeled as one supercomputer as an aggregated device. So there are data centers with over 10,000 physical servers that have been monitored quite comfortably this way. And we use the open source host sFlow agent to do that at SCinet.
So since you're at a pausing point here, Neil, Brian has a question. Isn't NetFlow looking at each packet rather than sampling?
Yeah, it doesn't. Well, to be honest, a lot of the NetFlow collectors are not able to do that. But the idealized NetFlow is to look at one-in-one. That's right, and that's why there are applications where, for example, if you're looking at a security log, and you absolutely have to see every last transaction, then there's a place for the NetFlow approach there. Absolutely.
And Jorge also has a question. What collector do you use? Does the collector have the capability to aggregate traffic? For example, aggregate traffic per source IP, per destination, or even per source destination pair. This could be used to find anomalies and attacks.
Yeah, we're using two different collectors here. One of them we call Traffic Sentinel, and it keeps about 200 different fields and can aggregate by any combination of them. So yes, MAC, VLAN, IP, TCP, BGP, AS paths, whatever you have there, you can aggregate by. And the other one is sFlow-RT, which also breaks out a couple of hundred different fields, but has the distinction that it operates in real time. Without building a traffic history. So they sort of, one of them is, so sFlow-RT is for what's happening right now, which is good for finding things like DDoS attacks. And Traffic Sentinel is for building an aggregated traffic history.
Okay, thank you.
So the next slide just goes into a little bit more detail on the difference between sFlow from switches and routers versus sFlow from servers and applications. So this is the part you're probably most familiar with, the packet headers being sampled and sent. When we get sFlow from a server, we're sending the CPU memory, disk, and IO stats as well, but also sending the hooks that are required so the collector can join the data model together. So even though the agents are operating independently, you can get a synthesized data model at the collector. And then when we layer in application visibility, It actually works a bit like the packet sampling, except that now you're sampling transactions, and you're much more likely to be doing one-in-one unless it's a very busy server. And once again, the application layer sFlow is required to send information that can be used to join it. So just as the network is being used to join the infrastructure together physically, so also it's actually the network layer that provides the join keys that put it all together in this model too. So the goal here, and this is what you finally end up with, is that you can correlate application layer experience with the infrastructure performance that's conspiring to deliver it. Now, sometimes people will turn on monitoring selectively. They'll say, oh, I'll just monitor the uplinks, or I'll just monitor the WAN links. And so the question does come up as, why go to so much trouble to monitor everything? And the short answer is that, in the end, it's much more trouble if you leave components unmonitored. But actually, there are also some pleasant surprises that you run into when you turn on full coverage monitoring. For one thing, you always have the context for anything new that happens in the network. So looking at a top talkers trend here, you always have the where, who, what, and when for any disturbance that you see. And that often means that you can solve problems just by picking up the phone and asking somebody, what were you doing at 8:23 this morning? You also can solve quite hard problems when you have full coverage. So the problem of tracing packet paths through the network just turns into a problem of lighting up where everything was seen. And the problem of locating every resource in the network just becomes a problem of saying, well, where was it seen talking into? So a lot of hard problems get easy when you have full coverage.
So we do have one other question that's come in before you advance there. Is the weather map view custom development or a standard feature of sFlow-RT?
Yeah, the weather map view was done by taking an existing drawing, as an SVG diagram, and then sFlow-RT is just animating the components of the SVG. So anything you can draw, you can animate. There isn't a drawing tool that comes with sFlow-RT. It just animates whatever it is you've already drawn.
Thank you.
So this current slide actually is also just circling back to sFlow-RT because it's an interesting example of something quite different from a NetFlow aggregation history. Oh, sorry, my screen just went to sleep. There we go. So when you have the packet samples being delivered straight from the switches, you don't have to do what the traditional approach is to decode and aggregate and store over time. You can do something quite different. So just as you could put it into Wireshark and look at the packet decodes, here you can also have some fun with an engine that reacts in real time to new information that's coming in. So there's a DDoS mitigation example, which will trigger in about 1/4 of a second. So you can actually cut off attacks using BGP or FlowSpec in less time than it takes for them to fully ramp up. So it creates a fun problem that the customers don't even know the attack happened, and the ISP has to explain to them, no, really, you were attacked, and they don't even have the evidence necessarily. Another one is to do triggered capture. So if there's just too much data to have all of it go through your deep packet inspection, then you can have rules for looking for unusual patterns and then trigger deep packet inspection, again with very short trigger times. Another one is looking at paths through ECMP fabrics. So it's like a sort of layer 2 trace route that works no matter what the kind of network you have. Another one is looking at real-time sort of topsiders and using that to push cached routes into a white box switch, so you can turn it into a full-scale internet access router. So that's a potential to save quite a lot of money with that one. And then looking again at ECMP fabrics, there are some significant performance advantages you can get by automatically marking large flows as bulk transfer priority. So actually marking them as at a lower priority than regular interactive traffic. And then finally, large flow steering is about actually relieving congestion that's caused when two large flows collide and take the same path through the fabric. So with just a small number of rules, you can nudge one of the flows onto a different path and actually get about 40% of throughput back from your fabric. So there's quite a lot of different things you can do when you have a real-time view with sub-second time response, but it's still with a global view over the whole system. And we keep thinking of new things to do with that. And everybody else is welcome to join in because sFlow-RT is free for non-production use. So for research and experiment, please go ahead and try it out. So that's all I had. There are some links here to different websites for different things. But if there are no more questions, I'll turn it over to the Georgia Tech guys.
So thank you, Neil. So while they're switching in, I do have one question I want to ask at this point. You talked about the scalability, which is great. What does that do to the VM that's collecting it? How bogged down does that become for, let's say, the upper end of being able to take in that data? Is this more of a CPU bound problem, or is it more of a network bound problem for the number of switches and servers that you quoted there?
When you have a typical campus with thousands of switches, then they're usually not all busy at the same time. And so there's actually, I think the control theory guys call it superlinearity. There's a superlinearity effect where adding more switches doesn't linearly increase the load on the collector. Plus you have the big slider. You can choose exactly what sampling rates to use. So you can match up the granularity with what you're looking for. And to be honest, with 10,000 samples a second, you can monitor almost anything. So it's a matter of choice as to what granularity you're looking at. So the difficult part really is more the same as with any other collector, that keeping up with the data that's coming in is not that hard. It's when somebody wants to do a query over the last month that you have to work a little bit harder. And that's where you want to have, flash storage if you can, for good performance on the disk I/O.
Okay, thank you. Whenever you're ready, Trevor and David.
All right, thank you, Jason. Thank you, Neil. I'm David. Trevor's going to chime in here in a minute. We're both full-time professional research faculty at GTRI in Atlanta. And we're going to be talking about a project that we've been working on with the measurement team and now the DevOps team at SCinet to prove out some real-time graph-based analytics for doing network monitoring using both Neil's tools and then also our own in-house graph database. So I come from a graph analytics background, and NetFlow as a standard makes a lot of sense to me as a graph. And so for this experiment, we take the information that's encoded in something like NetFlow v5, and we represent it in a directed semantic graph. So the vertices in our graph are going to be IP addresses in the network. The edges are going to represent flow events between two IP addresses. And we keep around some metadata that we associate with each edge, including the number of bytes that get transferred, what network protocol this flow was on, and then also some timing information. And for the purposes of this dashboard, we go ahead and collapse all of the flow events between two IP addresses and aggregate their weights so long as the protocol is the same. So this is our graph representation for the data that's coming off of the switches and routers at SCinet. And our goal is to study this graph in as close to real time as possible by computing as many metrics as we can to look for algorithms and metrics that have meaning for understanding the behavior of the network. The foundational technology that we developed at Georgia Tech is called Stinger, and it is not application specific. It is a generic graph database platform that also performs these analytics. And the focus here, there's lots of graph databases out there in the open source community and in the commercial community. Things like Titan and Neo4j are big players in this space. Our focus was on in-memory and near real time. So we're less concerned with answering questions about what happened in the past, but kind of like with sFlow-RT, we'd like to give a picture for what is happening right now in the state of the network. So we maintain this large data structure in memory that contains the entire semantic graph. And then we have a bunch of supported algorithms that compute, textbook graph metrics like between the centrality and connected components, page rank, and shortest paths for graph diameter, things of these sort. The Stinger platform does all of the data management for you. So you feed it edges. It makes sure that the algorithms get what they need, that they get scheduled and run, that the data is shared appropriately. And then the results of those algorithms are available through an HTTP interface on the backside so that you can write web dashboards like the ones we've been looking at, and we'll show you some of ours here in a minute. The software itself is written in C and C++, and so most of the algorithms are written in C++, but we've also created bindings for Python and Julia so that you can interact with the graph and write your analytics in different languages. And we support a couple of different APIs for sending data to the graph. And in this case, we're going to be taking NetFlow and converting it to edges, but you could imagine that your application might take tweets from social media or other data sources, streaming data sources. And as long as you can convert from your data format to some representation of a graph edge, then we can accept that. So this is sort of a notional architecture for what happens with Stinger. You start with your streaming data source on the left, in this case NetFlow, coming from the collector, and then we process that through an ingest engine, and that's the tool that takes the NetFlow events and translates them into edges and metadata. The graph-related information goes to Stinger, where we compute the graph metrics. We also save off some metadata to MongoDB so that we can recall it in the browser easily. And then the result of all of these analytics get populated into a web-based dashboard. Now, the examples you're going to see today are designed for a television screen, a monitor, because that's what's on the floor of SCinet. But these, of course, could be interactive in a browser if you so chose. I'm going to turn it over to Trevor here to talk about our setup at SCinet. We started with the measurement group in 2014, and Neil was really instrumental in helping us get off the ground and get integrated with NetFlow, and we'll be coming back for our 4th year this fall. Take it away, Trevor.
All right, so like David said, so we are really heavily relying on InMon. They send us NetFlow v5 to a server that we maintain on the SCinet show floor, which is running a FlowD. FlowD is a NetFlow daemon, essentially. It can do a lot of things: log to disk, log to a database, fire off triggers. But the way we're using it is just to open a local socket and then pass any data that it receives to this local socket. There's a Python script that we've written that's listening to this socket and is aggregating all of these NetFlow events, creating batches of edges for insertion into the network graph. So we're doing this at a rate of either every 5 seconds or every 5,000 edges. So this works out to, we get significant information in the graph pretty quickly. And then when Stinger receives a new batch of edges, any new batch of edges, it immediately computes analytics and updates its internal graph data structure. Depending on the complexity of the batch, that insert can take anywhere from 10 milliseconds to a second to update that internal data structure, and then the analytics typically complete in under 2 seconds, depending on size of the graph, complexity of the metrics, other factors. One thing that SCinet really helped us out with was figuring out where which pieces of the Stinger software we needed to work on and make better. One thing that we encountered during the course of our sign-up participation that we hadn't in traditional graph analytics situations was the presence of duplicate edges. So, in a typical network environment, there's a lot of traffic between two hosts that happens over and over and over and over. And the presence of these duplicate edges was slowing us down a decent amount, but we were able to make some changes and really kept up at wire speed in 2016, which was really great. And then for updating the web interface, we have a Python script that pulls analytics information from the Stinger RPC server. So the Stinger server supports basic queries like give me the top 10 nodes with the highest page rank degree, between the centrality, degree information. And so we make those queries, store all those results in MongoDB about every 5 seconds or so. And then the web application will pull a separate API that reads from this database. So we have real-time and historic information about these graph analytics. So here's an example of this dashboard that we run during the course of supercomputing. We have 4 top 7 lists of metrics on the left. So we're showing page rank, edge velocity, vertex in degree, and out degree. We do a reverse DNS lookup on each of those IP addresses that we store in the graph and display that to the user interface. Predictably, most of the top hosts at supercomputing are SCinet internal hosts, but we're really able to see some central nodes in this graph, like the name servers, InMon server, many of the wireless nodes, and a few security nodes. So we're able to pick out really nodes that are central to the operation of this network. In the top right, we see some statistics about the operation of this UI. It looks like this screenshot was taken towards the end of the conference. Thursday, it had been up for 7 days and had seen just over 1 billion flow events over that time. So the total graph had just about 6 million hosts with 210 million edges in between all those hosts, with overall flows of about 1,500 a second. That was a good, decent amount of traffic, and we're happy that this was able to keep up. There's a map in the bottom right that just does reverse or geolocation of IP addresses to to show, geospatially where some flow events are occurring. Here's some more information and easier to read metric lists. Like Neil said, the show saw over 3 terabits per second throughput in SC16, which was really great, and a peak of over 10,000 net flow events per second. That's a decent amount of traffic to be able to do real-time analytics. And during this time, our dashboard kept up with a delay of no more than 5 seconds, so we can really see some great real-time information about the network. I'll turn it over to David for our other UI.
Yeah, so 2 years ago at SC15, we started thinking about how else we could represent the data that we were seeing, and we had somebody suggested that we take a look at booth-to-booth traffic, because there are some demos that where certain booths have hooked up to transfer between each other, or to transfer out somewhere else and through a third party. And so we wanted to see, if we could visualize that in a way using the tools that we had built. And so a colleague of ours here at GTRI put together a tool to create an SVG, like Neil's weather map, to create an SVG of the show floor based on the drawings from the conference vendor. And so we took that, and then we wrote a NetFlow to booth map converter that would take the flow events, translate the IP addresses, look them up in the database for SCinet and figure out which booth they go to, and then offer that up as an API. And so this is the 15 booth map. Looks really nice. It fit nicely on the screen. The SC16 venue has a funny shape to it, and so it's a little bit harder to get on to a TV. But this is that booth map. And so we proved this out in 15. It was really nice last year in 16 that Neil came to us with sFlow-RT and said, my tool does all of these things that you guys hacked together last year. So can you just use it? And so he set us up with basically a cloned API of the thing we had created, and was able to feed us our data directly from sFlow-RT. So we used that last year. The booth map SVG, we created sort of this domain-specific language to describe where a booth is on a show floor, and this is an example. And then wrote some code to turn that into an SVG that we could animate with D3. Of course, we know now that we're a little bit smarter that this information is actually in the SCinet database, and so we don't necessarily have to do it all ourselves, but at least we know that we can. And then, yeah, we've added some hover tooltips to show vendor names and other information about the flows. And this is really nice because it puts the data in a geospatial layout that is more easily understood than subnet masks. And in fact, when we first debuted this 2 years ago, it alerted some of the folks on the security team to some potential issues because we were seeing flows between booths that didn't make sense based on the context of who was working with who. So we think that it's a good idea to consider visualizations that take that data out of the network space and put it into the physical space in real time. And our Stinger graph database is open source with a BSD license. We maintain it out of GTRI here. I'll caution you if you're a network person that we had to, as we described, write a lot of code to go from the network application to Stinger itself. But I don't know if that's posted out there, but we would give that away if you asked for it. So thanks for listening.
Okay, well, thank you guys. I have one question for you before we just open it up for general questions, and I'll remind everybody, just type your general questions into the Zoom session. If I remember correctly, since I was there in 14 when you were first starting this, how much data were you expecting, and then how much data did you end up getting? I seem to recall that some of your summations about how much you were going to get was a little bit off in the beginning, so you sort of had to readjust and prepare for the fire hose a bit better.
Yes, absolutely. When we came in 14 because we wanted a data source that had a high enough volume that we could get performance data to see where our tool was breaking. And in 14, we learned that it was breaking pretty much everywhere. So the data in SCinet was at least an order of magnitude larger than we were expecting, and showed us all the places where we needed to go back and optimize. I'm happy to say that in 15 we had cleared up the major issues and had a much better experience. And by last year, we had worked out the last of the pesky little performance optimizations around the types of things that Trevor mentioned. So one of the difficulties of developing research software is that when you're working with synthetic data or you're working with non-representative data, you will optimize for things other than maybe what your real application is doing. And we had optimized for all the traffic we had seen, but it wasn't until we got to SCinet and saw things like duplicate edges, and even IPv6 threw us for a loop. So those sent us back to the drawing board to figure out how to improve our tools. And that's really, I think, where the value from these types of field experiments comes.
No one ever expects IPv6.
Nope.
All right, well, thank you guys. And I'll impose upon Ken, because I just remembered that Ken was going to show sort of an example from Penn State, because, hey, we just don't do this stuff at SCinet. Some people actually go and adopt this and use this on their campus networks. So I don't know if you're still listening, Ken, but if you want to show the Penn State RT example.
Yeah, I'll flip over to that right now. Let's see this here. So yeah, we took pretty much what was going on at supercomputing and said, how can we deploy this across our campus? So we supported NetFlow, sFlow, IPFix, and whenever we had to stop monitoring music downloads and our security group moved away from NetFlow and they went straight to full packet capture with like a Gigamon or something, we could really turn up sFlow all over the place, and we were deploying it across the state among all our edge and aggregation switches. And then internally, it really didn't matter what our core was, whether it was a NetFlow or sFlow-based core, we could really collect anything. So we thought we could take a look at what we did at supercomputing and deploy it. So this is our just border weather map that we have running with our different connection out of Chicago and then our other connection through Philadelphia. Can you see this weather map? Sorry, I just okay. So this is upside down. It's bottom up design, not top down, but I don't know. So anyway, you have all the different peers down at the bottom here, but you can highlight any one of these links like Neil was saying, and you can watch a live flow going on. And just going off the screen, there was a big, probably a perf sonar test going on the left-hand side over here. But that's the kind of thing we're able to take and just mimic what was going on. Either, we had our Netflix cache. I need to update this map. This was actually moved out to this router now. But anyway, we have some other things like that where we've been able to deploy internally. Something we custom built was taking the data like this and breaking down our border network. We call this Border Dash. This is just a live real-time ticker of what's going on, where it's coming in, coming from. So we have our connection out of Chicago here, which we're running about 12.5 gigs right now. But then you break it down into all the different peerings we have. So these are just broken down and coded by different VLANs coming in. So you can take your traffic in, even at layer 2 with sFlow, and you can take a look and break that down and really see what's going on. I should probably kick off a big bandwidth test here, but anyway. We have our telephony link at the bottom here. This is just voice traffic coming in through our Philadelphia. Then we have our second connection through Kimber, our state network, broken down into the different services they offer. So you can actually break this stuff down pretty well and really understand what's going on. We also do some direct peering with other universities like Iowa, Northwestern, Illinois, Indiana. We're looking at Michigan State, and University of Chicago, and some other schools to do direct peering with and we should have ESNet peering turned up in the next week or two as well. So this is just an individual graph to break this down. Then internally, we said, well, how much traffic are we getting, through our internet connection? But here's our broken down to the same thing, sFlow-RT based on the different cache engines we have on campus. So you can actually see the number of traffic right now pushed through there just for my caching servers. So you can really break this down a number of ways and divide this up. Here's a pretty psychedelic graph coming up, but what this really shows is the amount of traffic coming in from Google, coming in through the first tier is the AS path is the top. The second tier is what border interface is coming in. The third tier is what type of traffic it is. And then the fourth tier is what supernet it's going to. So Google being the top, students being on campus, you can see how this traffic is coming in through both border connections. It's mostly HTTPS traffic, and most of it's going to wireless networks right now. So you can really understand that this is a sFlow-based job that runs in the background, then draws this graph every so often, and you can see how much traffic is actually going down. And what's funny is here's Valve and Steam, the video games. You can see they're both going to residence hall and wireless networks. And this is just the top 25 ASs coming into our network right now. So we've been able to mock this up pretty well, and we want to turn this into a real-time graph, hopefully for supercomputing, and get this built as well and be able to parse this out to be able to show really what's going on, or to carve it out so you only see just a certain booth data so you can see certain things like that. So really, as the data is coming in, and whether you're dealing with a few fields in a NetFlow 5 or you're dealing with a couple hundred through what sFlow can decode, it's pretty amazing when you can divide this up. It's almost like doing a database query for a certain specific thing you want to find. You can do that with flow data a lot. And we've done that quite a bit on our campus here. And since we have visibility all the way from the border all the way to the edge, with mostly sFlow, but we have some NetFlow as well, that we can actually troubleshoot things pretty well. So things we've applied at supercomputing can definitely be applied at a campus level, as well as we do this on our Science DMZ as well. We have access all the way to the edge of every research report on our Science DMZ. So anything else, Jason? I'm not sure what else.
No, I think that's pretty interesting.
Scaling piece here. So all our sFlow coming in from all over the state, 25 campuses, is roughly around 28 megabits a second. So you can see sampling at standard rates based on the defaults in the switches. You can see it's not very much traffic coming in because it's sampling packet headers. It's not building an IP cache on the router and doing the processing there and pushing it off. It's built in hardware and it's pushed back to a server for analysis. So,
and how many switches and routers would that encompass there?
I think right now this is a couple hundred, almost 1,000, but we're looking to scale this out to close to 3,000 by the end of the year. So,
okay. Well, thank you, Ken. We did have one question came in. It came in from Neil, though, so I don't know how legitimate we want to be here. Could Stinger graph rank hosts by number of hops from blacklisted addresses where the blacklist obtained from a security company?
Yeah, Neil. So that functionality is in there. We haven't tried that out at supercomputing, but you can specify a list of vertices that you want to see a hop count for, and it'll keep track of that at every iteration. So if you'd like to bring some IP addresses in November, we can do it.
That sounds good.
All right, so thank you, guys. Does anybody else have any questions that they want to type in? And I'll remind everybody that we will post this online if you want to view afterwards. And if anybody does have any more questions about SCinet or supercomputing in general, I'm sure that any of these guys would be happy to answer. All right, so it sounds like we may be done for today. So thank you all for coming. Just as a reminder for next week, I need to look and see who's next week. Next week, it's going to be the University of Virginia, and they're going to be talking about a read-only root environment for scientific computing. So I will send out announcements as we get a little bit closer for that. Thanks, everybody, for joining, and we'll post this online. Have a good weekend.
Thanks.